Hey students, this video is going to go over a few miscellaneous things as far as this unit goes and as far as structures go. So first off, our Lewis structure video went over how we can have single bonds or double bonds. We can even make a triple bond if we need to make one of the atoms happy and up to 8 valence electrons. Single and double and triple bonds consist of sigma and or pi bonds. And this is just based on how the orbitals overlap in the forming of the bond. Okay, you don't have to know anything about how they overlap. I did put some pictures here and on the next slide to show you in case you wanted to have a little bit of extra information, but you just have to know which type of bond, the sigma or the pi, is found in a single, double, and triple bond. So a single bond is just where you have the one line connecting the two atoms. And sorry, I'm trying to get my tools here. So you have a single line between the two atoms, and because it's just a single line, it's just one bond, it's going to have one sigma bond. This is going to be the weakest of all of them because it's just one pair of electrons holding those two atoms together, and it's the longest bond. As we add more bonds, the bond between those two atoms gets shorter. A double bond is, as you can see up here with the O2, has two lines connecting the two atoms together. The first bond formed is going to be a sigma bond, and then the pi bond is going to be the second bond formed. It's just because those pi orbitals are oriented in such a way that they can't rotate around each other. The triple bond, like an N2 here, has three bonds or three lines between those atoms. The first one is the sigma bond. So it has one sigma bond, it has two pi bonds. This is the strongest of the three because there are three pairs of electrons being shared between those two atoms. And it's the shortest bond because those three pairs pull those atoms closer to each other. Okay, so this next slide goes into a little bit more about the sigma and pi. This is just for your information if you want it. You don't have to know any of the information on this slide. It's just showing you how those orbitals can overlap, creating a sigma bond or a pi bond, where the nuclei are, how those electrons are shared, where the electron density is, that kind of thing. So just look over this if you wanted to have a little bit more information about the sigma and pi. We've already gone over Vesper shapes, so I'm going to skip over these two slides. Okay. Now, the next couple things we're going to talk about are bond polarity and molecular polarity. And these are two different things. You always want to be careful and pay attention to if we're asking and talking about bond polarity or if we're talking about molecular polarity. Bond polarity is talking about in between the two atoms themselves. So for example, if we had carbon dioxide here, we're not talking about the molecule overall, we're talking about the bonds in between the two atoms and if the bond itself is polar or nonpolar. If we're talking about bond polarity, we're looking at the difference in electronegativity. Electronegativity, remember, is the ability to attract electrons. If something has a really large electronegativity versus something that has a lower electronegativity, the atom with the larger electronegativity can pull the electrons closer to itself. The way that I liken this is if I'm going to be playing tug of war. So here you can see there's tug of war over the electrons. These two characters are playing tug of war. Well, I happen to have a twin sister, and if I was going to play tug of war over an electron, because we're very similar, we would share those electrons equally and evenly between us because one is not stronger than the other. We're not going to be able to pull the electrons more towards me or more towards my sister. So that would be a nonpolar bond because our electronegativities, our strength, is similar. If I was going to play tug of war with the rock, who do you think is going to win the electron? Thanks, guys, but it's not going to be me. It's going to be the rock. He's going to be able to pull those electrons closer to him, and I'm not going to have as high of a pull for those electrons. So this would be a polar bond because he would be able to hog those electrons, have those electrons more towards his center than I would be able to have those around my center, okay? So bond polarity is based on an electronegativity difference. A polar bond means that there are opposite ends, okay? And this is going to be a larger difference in electronegativity. Okay, so if they are different atoms, they are going to have a polar bond. Now remember, these are only between non-metals, because metals and non-metals form ionic bonds where it would actually form a full positive and a full negative ion because there's a complete transfer of electrons. Polar and non-polar bonds form when the electrons are shared either equally or unequally. Polar bonds, because they're different atoms and there's a difference in electronegativity, there's going to be an unequal sharing of electrons. There's an unequal sharing of electrons because one thing has more electronegativity than the other. So if we look at this picture of water over here, water we know has a really high electronegativity because it has low shielding, but it has a large Zeph. Hydrogen has a very low Zeph. So even though the electrons are close to it, the low Zeph means it has a weak electronegativity. So the oxygen is going to be able to pull those electrons closer to its nucleus than the hydrogen can. So it's going to form a partial negative charge, shown by this symbol up here, because it's going to have the electrons, which are negative, around its center more than the hydrogens, which would have this positive, slightly positive charge, denoted by this dipole, as we say. Okay. Now, a nonpolar bond forms when there's a small difference in electronegativity. So these ones are going to be where the bond, the covalent bond, remember this is just covalent bond exists between two of the same atoms. Or the carbon-hydrogen bond, as we see down here, the carbon-hydrogen bond. Because the carbon-hydrogen bond, even though they're not next to each other on the periodic table indicating same electronegativities, they are very close in electronegativity values where the carbon would not hog the electron significantly more than the hydrogen would. As you can see here in this picture of Cl2, the electrons are shared equally between those two atoms. Because they're shared equally, it would be a nonpolar bond, indicating that there was a small difference in electronegativity, or no difference in this case. Okay, so polar bonds have an unequal sharing of electrons, and they are going to form between two different nonmetals. The nonpolar bonds have an equal sharing of electrons, and they are going to form between two of the same atoms, or the carbon-hydrogen bond. And this is really, really, really important. Students always make mistakes with bond polarity and molecular polarity, so make sure you know the difference. With bond polarity, we would indicate for polar bonds only which one would be a slightly negative and which one would be a slightly positive by putting these dipoles here. Okay, so the more electronegative elements, so we would again follow the trend for electronegativity, which increases up and to the right. So you would see, based on electronegativity trends, which one is more electronegative would get this dipole here, indicating that it was slightly negative. The one that had the lowest electronegativity would get this dipole here, indicating it was slightly positive. This only goes, these dipoles only go on polar covalent bonds, only on polar covalent bonds. Nonpolar bonds, because the electrons are shared equally, one would not be slightly positive or slightly negative. So these are only on polar covalent bonds, okay? Now, molecular polarity is different. With molecular polarity, we are looking at the molecule itself and seeing if there is an unbalance of electrons in the molecule itself. So if to have a polar molecule, we'd have to have different ends on the molecule, which is like the CH2F2. When we draw it, we would have an H and an F and an H and an F. seeing how there's different atoms, there's hydrogens and fluorines on the end, on the outside, that would indicate that this is a polar molecule because there's an unbalance of electrons, or there are lone pairs on the central atom, such as water, which is this structure here, okay? Lone pairs on the central atom indicate that it's a polar molecule because there's an unbalance of electrons. And the electrons are not being shared equally across the molecule. Nonpolar molecules mean that the ends are the same, so the outside atoms are the same, and there are no lone pairs on the central atom. So with carbon dioxide, for example, carbon dioxide looks like this. There are no dots on the central atom, and the oxygens are the same on both sides. It doesn't matter that the bond is polar. It doesn't matter that the bond is polar. The molecule itself, the overall molecule, is symmetrical. The ends are the same. There's no lone pairs on the central atom, and so this is a nonpolar molecule. Methane, CH4, which looks like this, is a nonpolar molecule because all of the ends are hydrogen. So all of the ends are the same, and there's no lone pairs on the central atom. Notice this here, or, and this here, and. Polar molecules, one or the other, the ends are different, or there are lone pairs on the central atom. Nonpolar molecules, the ends have to be the same, and there are no lone pairs on the central atom. This is molecular polarity. Bond polarity is based on the electronegativity difference. Molecular polarity is based off of these two factors. We've already talked about resonance in the Lewis structure video. We've already talked about polyatomic ions in the Lewis structure video. So I'm going to skip over this slide. So practice problems. We're going to draw and identify a couple of these, and we're going to talk about the Vesper shape, and we're going to talk about the bond polarity and the molecular polarity. I'm going to change my color here. So carbonate ion, CO3 -2. So carbon, again, has 4 valence electrons. Oxygen has 6 times 3 is 18. So that is 22, but we have a -2 charge, which means we add 2 electrons. So we have 24 total valence electrons. Don't forget, when you draw your Lewis structures, number 1 rule, put the electrons in the bucket. Count your valence electrons and put them in the bucket. So we're going to put our carbon in the center. It's the least electronegative, and we're going to connect the oxygens to it, such as this. We've used 2, 4, 6 electrons in our structure. So we'll subtract those out. We have 18 left. Those are going to go on our outsiders. 2, 4, 6, 8, 10, 12, 14, 16, 18. So we have drawn and used all of our valence electrons, but don't forget step 5 to make sure everything is happy. Each oxygen has 8 valence electrons around it now, but the carbon only has 6. So we want to make sure we erase a pair, a lone pair, whoops, and let me add that dot back. And then we want to draw our double bond, but because this double bond could exist in any location, we want to draw resonance using dotted lines to all of the other atoms where that double bond could exist. We want to put brackets around it because it has resonance and because it's a polyatomic ion. So once you draw it, you can identify the Vesper shape. So how many bonded pairs and how many lone pairs are around the central atom? There's 3 bonded pairs, no lone pairs. That means it's a trigonal planar. And then we've got to determine bond polarity. So with bond polarity between the carbon and the oxygen atoms, the bond, they are not the same because it's a carbon-oxygen. It's not carbon-hydrogen, so that makes it a polar bond. So because it's a polar bond, we need to draw dipoles to indicate the distribution of the electrons around the molecule. So it's a polar bond. So that means that oxygen is most electronegative, so it would get a slightly negative dipole. The carbon being less electronegative would get the positive dipole. And then we want to determine if it is a polar or nonpolar molecule. So we look, are all of the ends the same? Yep, they're all oxygen. Are there lone pairs on the central atom? Nope. So this is a nonpolar molecule. All right, let's look at SiS2. Si has 4 valence electrons. S has 6 times 2 is 12. So that means we have 16 total electrons. Which atom, the Si or the S, is going to go in the center? Si would go in the middle, connecting the S atoms to it. So we used 4 electrons that time because we only made 2 bonds. So we have 12 left. Where are those going to go? They're going to go on the outsides. So 2, 4, 6, 8, 10, 12. So we've used 12 more electrons. We have 0 left. Don't forget step 5 to make sure everything is happy. The silicone is not happy because it only has 4 electrons around it. So we need to erase a pair of electrons and draw a double bond. But silicone is still not happy because right now it has 6 electrons. So we need to erase a pair from this other side. Oops. And add that dot back. And then we've got to make a double bond between the silicone and this sulfur over here. Now it is happy. Everything has 8 valence electrons around it. What structure, Vesper shape is this? It's going to be linear because it has 2 things bonded to it and no lone pairs. So look at the bond polarity. We're looking at the silicone-sulfur bond, looking at the electronegativity differences. These are not the same atom, and it's not carbon-hydrogen, which makes it a polar bond. Which one is more electronegative? The sulfur is more electronegative, so it would get the negative dipole. The silicone is less electronegative, so it would get the positive dipole. And let's look at molecular polarity, so the overall molecule itself. Well, the ends are the same. There are no lone pairs, so it is a nonpolar molecule. Okay, so let me erase this here. We will do the OF2, and then you can practice on the next slide by yourself. So OF2, oxygen has 6 valence electrons, fluorine has 7, times 2 is 14. So we have 20 total valence electrons. Which atom is going to go in the center of our structure? The oxygen, and we're going to connect the fluorine to it. So we used 4 electrons, so we have 16 left. That means we're going to put them around the outsiders, 2, 4, 6, 8, 10, 12. Let's subtract that from our list. We have 4 left. That means that they are going to go on the oxygen like this, and we used up all of our valence electrons. Make sure everything is happy. The fluorines have 2, 4, 6, 8. The oxygen has 2, 4, 6, 8. So everything is happy. So let's discuss the Vesper shape. There are 2 atoms bonded to it and 2 lone pairs. So this is a bent molecule. Let's discuss bond polarity, the oxygen-fluorine bond. They are not the same atom, and it is not carbon-hydrogen, so it is a polar bond. Which one is more electronegative, the oxygen or the fluorine? Fluorine is more electronegative, so it gets the negative dipole. Oxygen gets the positive dipole. And then let's determine molecular polarity. The ends are the same, but there are lone pairs. Since there are lone pairs, that makes it a polar molecule. Okay, so you can see how we do that on those. You can practice on the next slide. Let me know how you guys do. If you have any questions about bond polarity, molecular polarity, Vesper shapes, let me know so I can help you guys out. All right, thank you.